We're going to talk about a couple concepts today. We're going to look at first transformation of functions, and then we're going to look at composition of functions. Now, transformation of functions is really just taking a basic standard function and moving it around. We're going to look at shifting it left and right, flipping it, and then stretching and shrinking it. Where we have to first start off with, though, is what our basic functions look like. And we're going to look at four today. These are four you're going to see a lot of. Our first one is f of x equals x squared. Everyone should know basically this is a quadratic function and it makes the shape of a parabola. And we need to know the general look of this parabola so that when we do stretch it, we can just kind of move it around and sketch it real quick. Our second function is something called the square root function. F of x equals the square root of x. And this basically starts at the origin and goes up and to the right. Notice we start here. So our domain is from 0 to infinity. Our range is from 0 to infinity as well. And there should be arrows on these. These should go infinitely in the direction they're trending towards. Our next function we're looking at is the cubic function. F of x equals x cubed. And this makes a nice little, almost an S shape if you want to think about it. Again, this is one of those ones you need to be able to look at and just tell exactly what it's doing. And the domain here is negative infinity to infinity, and the range is negative infinity to infinity as well. And the last one we're going to look at today, the basic function, is the absolute value function. F of x equals the absolute value of x. This makes a nice little V. Our domain is negative infinity to infinity, because we can plug in any number. But our range is 0 to infinity, because absolute values only give us positive numbers. Let's talk about our first type of transformation. We're going to get vertical shifts. We have f of x plus c and f of x minus c. Notice that the c in this cases are both outside of our regular function. So, in this case, I'm going to shift up when I add a number to my function and shift down when I subtract a number from my function. Let's look at this example. Y equals x squared minus 5. Well, we know y equals x squared is our standard function. It's a parabola. It makes our wonderful U shape. The minus 5 is outside the function. Think of PEMDAS, okay? If it was inside the function, you'd be subtracting the 5 first. In this case, our rules of PEMDAS say square first, so the function is there by itself, then I'm subtracting 5 from it. Well, in this case, this simply says shift the graph down by 5 units. So I took my standard graph, and I pushed it down 5 units. So notice my vertex is down at negative 5 now. If I were to shift it up by 5 units, this entire graph would shift up to positive 5 and make my U there. The next thing we're going to look at is a horizontal shift. This is very similar. This is f of x plus c and f of x minus c. They read the exact same. The difference is the c's inside the function this time. Now this one's a little bit tricky because this does the opposite. If I add the c, I actually shift to the left, and if I subtract the c, I shift to the right. So let's look at y equals x plus 3 quantity cubed. Notice the 3 is inside the parentheses, so I'm actually adding 3 before I'm cubing. So I'm adding the c before I do the function. That means it's inside of the function. So this means I'm shifting left and right, not up and down. Now again, the plus 3 tells me to shift to the left. Remember, it's opposite when it's inside. So I'm going to take my standard graph of my cubic graph, which was our little s, and I'm going to shift it to the left by 3. So originally it went through the origin. Now it's going to go through the point 0, negative 3. And again, we just want to be able to give quick sketches of these. Alright, we're not going to sit there and try to plot dozens of points right away. We want to get a general idea of how these shifts are working. We'll get more precise in some problems in this section, but mainly we want to get the idea of what's happening. Next we have reflections. Okay, reflections are basically mirror images of things. All right, we have two types of reflections. We have a reflection about the x-axis and a reflection about the y-axis, and they work differently. Just like we added this c on the outside or on the inside of the function, in this case reflections deal with minus signs. And if I reflect around the x-axis, I'm going to have the minus sign on the outside of the function. And if I reflect around the y-axis, I'm going to have the minus sign on the inside of the function. Let's look at the example. We have y equals negative square root of x. The negative is on the outside of the function. So that means I can reflect, or I take a mirror image around the x-axis. Well, we know our square root graph usually starts at the origin and goes up and to the right. So the mirror image around the x-axis flips it downward. And notice how this graph starts at the origin and goes down and to the right. Similarly, if I look y equals negative square root of x, the negative is on the inside of the function this time. That means I'm reflecting around the y-axis. So instead of starting at the origin and going up and to the right, I'm going to reflect that this way, left and right, and I'm going to start at the origin and go up and to the left. The last thing we're going to look at as far as shifting and reflections and whatnot is actually stretching and compressing the graph, or stretching and shrinking the graph. And in this case, I'm going to, instead of my negative signs, I'm going to have my number c again, but I'm not going to be adding or subtracting it, I'm going to be multiplying it. And in this case, if c is inside the function, this is a horizontal stretch if c is between 0 and 1, and a horizontal shrink if c is greater than 1. Let's see how that works first, then we'll come back to the vertical stretch. I'm going to give you three functions here. I'm going to give you y equals the square root of 16x, y equals the square root of x, and y equals the square root of 0.1x. Y equals the square root of x, this is the blue graph. That's the one we're used to looking at, okay? Now, y equals the square root of 16x, c is greater than 1, so it shrinks. So basically, notice this graph looks like something happened to it. Really what happened is I took it all the way from the right, and I pushed it from the right towards the origin, towards the y-axis. I kind of shrunk it down, so I took it over here and brought it this way. It looks like it's increasing a lot steeper, but it's actually being compacted. Now, think of this y equals the square root of 0.1x. This is my green line here on this graph. Alright? Well, basically what I'm doing is I'm taking this graph, instead of pushing it to the left, think of a rubber band, I'm taking and stretching it to the right. So it's a lot less steep. It's being stretched out that way. And we know whether to compact it or stretch it or shrink it based on this c, this number inside. And again, this works opposite for the horizontal stretch. If this is 16, this is greater than 1, it's going to be shrunk. If this is 0.1, it's between 0 and 1, it's going to be stretched. Now let's see how this works also for a vertical stretch. In this case, the c is on the outside. But again, this works how you would normally think it would work. If c is greater than 1, it's stretched. If c is between 0 and 1, it's shrunk. So let's look at our last example here. We have y equals 16 root x, y equals root x, and y equals 0.1 root x. Again, the blue is our standard graph, our square root of x. This 16 basically is multiplying all my y values. This is going to get a lot bigger. Think about it, just this piece is being stretched all the way up. You're not even seeing most of this graph because it's being stretched so high. Whereas y equals 0.1, I'm actually collapsing. I'm trying to push it down towards that y-axis, so it's basically being pushed down, kind of like a car crusher, if you want to think of it that way. Now, we went over very basic examples here. However, please remember, we're doing a lot of things with these graphs, alright? Now the one thing I encourage you to do as you work through these is remember your order of operation, okay? Because some of these are going to happen before others. So say if there's a 16 square root of x plus 5, well, according to your order of operations, the x plus 5 has to happen first, so the horizontal shift would occur before the actual vertical stretch. Think about those things, give it some practice, and I think you'll find that you'll see a lot of the patterns developing. Now, in this next section, I really want to focus just on composition of functions. Composition of functions is really where you take two functions and make one function range the domain of the other function. Now, you've seen the f plus g, the f minus g, the f times g, the f divided by g. Those are all very basic, simple, straightforward. This is the f of g of x and the g of f of x. Let's look at the notation. G of f of x. Well, I'm told that f of x equals x squared and g of x equals 2x plus 1. Basically, what's going to happen is I'm going to take this inside function, that's where I'm going to start, f of x. Well, instead of g of f of x, I'm going to replace my f of x with what f of x is. F of x is x squared. So this is g of x squared. Well, basically what this tells me anywhere I see x, I'm going to replace it with x squared. So g of x was 2x plus 5, so wherever I saw the x, this is 2 times x squared plus 5. and I'm simply going to reduce. This is 2x squared plus 5. Now, f of g of x is going kind of in the other direction. This is f of g of x. I'm going to start on the inside. I'm going to take my g of x and write it out. G of x is 2x plus 5. So this tells me for my f function, wherever I see x, I'm going to replace it with 2x plus 5. So f of x was equal to x squared, according to our original function. So f of 2x plus 5 is 2x plus 5 squared, and you can FOIL this out or use your formula to get 4x squared plus 20x plus 25. Please note how different these two are. Okay? Occasionally they'll give you the same, and we'll talk about that later when we talk about inverse functions, but most of the time they're going to wind up differently. Good luck this week. Let me know if you have any questions.